Well, we're going to start with the idea. Do you have any questions? I know that Jean-Pierre has a question, and it's perhaps a couple of minutes if there's any questions before I get back into the second half. Okay, Jean-Pierre.
I can ask a question right now.
Sure.
Okay, so I would like to come back to the very first figure you gave about chemical abstract service, CAS, number of molecules.
Mm-hmm.
You mentioned 150 million. My question was about part of it is related to so-called prophetic structures. And CAS has taken the habit to abstract the compounds that are patented, encompassed by a patent, which are not being made. You know, so R1 is this one, R2, R3, R4. We generate tables in a patent, and part of these molecules are made, and the rest is just so-called prophetic or virtual structures. So I don't know how much is influencing the number you gave.
Well, Jean-Pierre, the first thing, of course, one has to remember that not all these compounds are organic compounds. We have actually materials, composites, everything which you can call chemical. And probably the great majority of the organic compounds are heterocycles, which are not really looked at so much. Now, getting to your point, it's a kind of interesting thing. People are not aware of that. I think the interesting point is not the total number, 150. It's the exponential growth, where there's a provision now that these numbers will double every 4 or 5 years. So I don't really worry about the absolute number, but the doubling up in such a short time. Any other questions? Okay, so let's start. Well, so the first thing which is here is that we are looking at a new way of doing organic synthesis. We're still doing the same reactions, the same practical way. Tactics will not really change very much. They'll probably get better. What is going to change is that we are now looking at practical, efficient, scalable syntheses, and this has consequences on the way we are thinking about doing synthesis. And to do this, we now require new tactics, that is new methods, new reactions, and we need new strategies. Okay? So what are the new criteria you would look at for a good modern organic synthesis? You will stop a step count, preferably under 10. In fact, the syntheses we saw yesterday and the day before, the syntheses in the pharma industry, most of them don't get to 10 steps. And that's why they are interesting to make compounds. We now have a kind of a rule. If you go over 20, the very most, you probably get serious criticisms before it's published, and if it will be published. So we try to look at this scale for 20. The overall yield should at least be 1%, which is much higher than it used to be. But even 1%, we can see many examples where 1% is nothing. It's 10, 15, 20% overall yield. You have to have multi-gram quantities at the end. In fact, if you want to be clear, you show a round bottle flask and a photograph of the compound in the flask to show, yes, I've made all this amount of material. Okay? And a second thing, which is called reproducibility. This is being seriously questioned and goes back to the old. If you do a synthesis of 170 steps, nobody's ever going to check on that really. So you don't really know how many steps actually worked with that yield. Did it really work? Now we have to have a guarantee. Many people are questioning this point here, and we have to avoid that completely now. So, Yesterday it was mentioned, I won't pick on repeating, scale up, scale out, scalability. Lab size, and you start going up, you can see the quantities, kilogram, and finally you get to some kind of interesting scale in the industry. I'll just point out that in São Carlos we now have, Kleber is the owner, it's a 50-litre batch reactor. That seems kind of funny to people who do flow chemistry are going also into batch chemistry at the same time, but there's a reason for that. And in the ASSERT lab, where Jezibar works, he also has a 50 and 100-litre batch reactors. So this has got to São Carlos to do batch chemistry. We're on this kind of, no, maybe on this kind of scale here. Okay? Well, cost, what the customer wants, and the chemistry. Scale up. Scale up is here. You get bigger and bigger and bigger and bigger. If you can't do that, you do scale out. Scale out would be get 5, 10 of these kind of reactors side by side and just repeat the reaction in the same kind of reactor, but just 5, 10 times. This is not really a new idea. I did my PhD, we did some scale out. So you could actually get quantities also doing that. Just a few comments. Methodology is getting more efficient. I will make a strong statement, which people have questioned. I say there are no new reactions. If you look at the reactions, most of them are actually very old, at least 50 years, 100 years, maybe 200 years. And if you see what seems to be a new reaction, it's just a simple variation on an old theme. In other words, Grignard, you use magnesium. If you change magnesium and put a different metal there, it's still a Grignard reaction to me with a different metal. The reaction is not really new. Anyway, no reactions. But there are many, many improvements on the old ones. Here we go. Metathesis, old reaction. But we have new catalysts. Cross-coupling, a very old reaction. We're talking about 50, 60 years ago when these reactions were developed in industry. But we have new catalysts which are much more efficient than the old ones. So we've got a great improvement on the old reaction. Lots of enantiopure chiral catalysts. In other words, new reagents for old reactions. We can also do new ways of performing these old reactions. We had ultrasound, a little bit. The microwave is perhaps over. It's stopped being a novelty. It's now just a kind, you have a microwave in the lab and use it when you need. But it's not really a novelty anymore. And of course, continuous flow chemistry, equipments are available. You can see one out there. If you want to see it, Cirrus. And interesting that people are finding that photochemistry and electrochemistry are really important techniques, and they're coming back with a real bang. We're doing photochemistry in São Carlos. Electrochemistry, we have also an electrochemical apparatus which you can hook onto the flow chemistry. So these are two new ways of doing reactions. So let's talk about the computer. So you might look. That used to be the best use of a computer. You take out all that rubbish and you can use it for a churrasco. And that was the best use for a computer. Okay? Well, maybe we can do a lot more now. Let's just see. We can do retrosynthetic analyses, the reaction choice from Grybowski and Cynthia. Just one example. This I'm going to come back to. We have robotics and synthesis machines. Leroy Cronin in Glasgow is perhaps the person that's really getting further forward on this. He has some videos. So if you want to find out about Leroy Cronin, Lee, look at his homepage, get the videos. It's YouTube. You can play these videos and you can see him making Viagra on a machine. You just switch it on and it makes the several steps of the Viagra synthesis. Okay? high throughput experiments, design of experiments. Perhaps this person, Klaus Jensen, who is a chemical engineer, but he leads a fantastic group of scientists at MIT, and obviously has lots and lots of money from pharma industry. We can do machine learning, and we can now do something which I personally aren't wild about. If you can't discover the mechanism, then calculate it. And we all have to calculate the mechanism, but having no idea whether it's actually true. But it's a great idea to calculate. And we also have continuous processing, basically in industry. This example here. I'll spend a couple of minutes on this. What do students usually do when they have to do a reaction? They go to SciFinder, find an example, don't bother to look at the substrate to see if it's similar to their substrate, and they just transport the experiment. I call that kitchen recipe. Yeah. If your grandmother used to make the cake, you usually make the cake the same way. It doesn't matter what's in the cake. If your grandmother said do it this way, you'll make the cake the same way. In Portuguese, receita de bolo. And then the person said, no, it's not that, it's a protocol. Wonderful word, protocol. And the reaction doesn't work because your substrate has got nothing to do with the example. So how do you get over that? There's now a program which could look at not 5, 10, 15 reactions of what you want to do, thousands. And they will find amongst these 1,000 reactions a substrate which is close to yours. So now you could actually choose a more correct reaction, a better reaction condition based on the similarity between what's published and your molecule. You can't find that by SciFinder, but this program will help you to find the preferred conditions. So there we are. There's Cynthia. Sigma Aldrich has now bought this from Grabowski. Not sure how much it is. And this is just a picture from Cronin's lab in Glasgow, where he's now using what he calls the chemputer, not more the computer. It's the chemputer, and you can get some videos to see what's happening. And you just switch it on, and you get reaction, 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 and you get the product at the end. And one of the examples is Viagra, which he makes on this machine. All goes back to Ed Berryfield's automated peptide synthesis in the 60s. So let's go on. We need new tactics and new strategies. How do we get better strategies? We have to substitute reactions which create only one carbon-carbon bond with reactions that produce at least 2 carbon bonds. So we prefer pericyclic reactions over simple additions and couplings. Second option, you can plan sequences in your retrostate analysis which involve one pot, as we saw with Robinson. You get more reactions from the same round bottom flask. You can do multi-component reactions. Just to give you an idea, the first obvious multi-component is the Strecker reaction, 1850. Once again, don't think we're doing new reactions. We are not doing new reactions. Domino cascade reactions, disconnections. Well, nature has always used domino reactions. If you look at biosynthesis, it's a sequence of domino reactions. So there's no novelty in doing domino reactions. We're just repeating what nature has always done. Well, strategic efficiency. I'm just going to comment that there's now even a publication, 2008, in which this person tries to quantify the efficiency of a strategy. I didn't get very convinced, but it's worth looking at if you want to find a little bit more else. So we need new directions in the new retrosynthetic efficiency. So, if you want to improve on retrosynthetic analysis, first of all, you must look at what the others did before. And then you should say, well, he did this analysis, 20 steps. I want an analysis now which will give me the same thing in 10. That's what we want looking for. And here's the reason. We can see that we can see that this quote is also several hundred years old. And if I have seen further, it is by standing on the shoulders of giants. You have to find out what the others did before you, and then you get on their shoulders and you can see further. I also ask, don't forget to cite them. Okay. This is for people who do organic synthesis. I do 1% of the activity using this, and the students do 99% of the rest. Here it is, 1% or 10% inspiration. But the rest, if you want to be a genius or do organic synthesis or be a success, you need a lot of perspiration. The main part is perspiration. Let's start. Finally, to see a synthesis. Now, clearly what I'm doing here is I'm having a choice of a person selection. Another person would choose other syntheses, recent ones. I've just had my choice, and I will show you some of this. So here we are. Thapsigargin, scalable synthesis, Phil Barron and his lab at Scripps. And you can see here what is the idea. But note a few things which you wouldn't have seen 20 years ago. Dihydrocarbon, but we have the price. So we now know immediately how much it costs to start doing the synthesis. And that is important, especially here for us. So we have the price, we have the starting material. The cyclized phase is when you put on the rings. We have one ring, we have two rings. The oxidase phase is we start here with practically only one oxygen, and we are going to put on 1, 2, 3, 4, 5. We have to put on 6 oxygens around the rings and a couple of oxygens outside. So we need a strong and good oxidase. Oh, jumped again. So perhaps I'll go back a second. So we also put in now basic questions to make sure it's worthwhile looking at these new syntheses. The old syntheses, you finished and you published, and you didn't explain anything to anybody why that synthesis was so important. Now you have to. Okay? One-pot sequences reduce the step count, and that is part of the reason that I chose this example, because there it is, scalable synthesis. Now when Phil Barron sent the paper, the manuscript to Jacks, he put the number of steps and said it was 11. And the referee said no, take it out of the title, take it out of the abstract, your step counts we don't believe. So he was, and this is not this is public. His students got really sorry about this, and they've published all this. They even put in the referee's comments, which I think is a little bit unethical, but anyway. so we have all this. This is, and what Phil Barron did was to go on and do a lot of one pot. Here we have 11 steps. Gram scale, so we have price, we have scale, we have the number of steps, well under 20, and we have a comment about the previous synthesis. Now that's not really true. The previous synthesis is Steve Lake, and Steve did the synthesis in something between 35 and 40. Doesn't make much difference, 35 going down to 11. So, where's the secret now on the one pot, which is the question which provoked all the discussion with Jacks and everything else. We have a lot of pot economy and a lot of one pot synthesis. Here's a great review by Hayashi, and you can see, look at the reactions. The famous Robinson annihilation, 1920s. The first and real key reaction. But what he does here, he does the reaction, and then he bubbles in oxygen. So you get two reactions for the price of one. You get the Roberts annihilation, putting on this second ring, but at the same time you get an oxygen atom put in. So two distinct and different reactions are done one pot. Okay? Next step. There's a bit of complication here, but you can see once again, you do something, and then comes the word then. Then you put in a different reagent and you do a different thing. Basically what was done here was to introduce this double bond in two reactions, one pot. So you do two reactions, one pot, and Phil Barron counts one step. So obviously step count is going down. But I agree with him. If you can get to do 2 or 3 reactions, one pot, the workup and everything else is eliminated. So I think it's a great idea to do one pot. Okay, then we go on now to this one, going down here. So he does a Burgess dehydration and then does an admix hydroxylation, one pot. So if you start to count really, 2 reactions, 1 step, 2 reactions, 1 step, 2 reactions, 1 step. So he counts 1, 2, 3 and doesn't count 6. And I think he's quite correct doing that. I would do the same thing personally. Once again, protection, then you do an oxidation with selenium dioxide. Once again, two reactions in a one pot. So he counts this as 1, 2, 3, 4. But you could say there are 8 reactions being involved. Next thing, gram scale, gram scale, gram scale, gram scale, and gram scale. Everything is gram scale. At least a gram, maybe 10, depends on the reaction itself. But they're all gram scale reactions. And then he does this, and the cyclized phase is now over. All the reactions which come now are oxidations. This is a kind of abstract itself. Here's the molecule, dapsygagin. It is a potent circuit pump inhibitor. This compound is nanomolar bioactive. Now that is interesting, important, and also a problem. The students can't make the compound in great scale because it's bioactive. They could actually have some problems with the bioactivity of the product. Okay, here's the previous work. This is Steve Lay. Number of steps to compare. Both started with carvlone or dihydrocarvlone. I just point out this is an example of what we call the chiral pool. And the question Giuliano asked yesterday, why do we use few enantioselective reactions to create? Because it's cheaper to buy or get carbon for free. What else? Key reaction, we have 2 key reactions, the Robinson annihilation and the Barton photo. The Robinson annihilation is the 1920s. The Barton work, which is a very simple example, 1957. Once again, 2 old reactions being used in a more modern view, and we'll see this constantly. All this chemistry involves old reactions, but done in a new way and better. Okay, what else? And here's the point about the oxidized phase. He's down here with this intermediate and wants to get here. Now you can see the number of oxygens, and this is not as difficult as it might seem. You use one oxygen to put in the next, and the next, and the next. And you just go around the ring putting in more oxygens. And you can sometimes get more than one oxygen for a reaction. So that's why the step count once again goes down. Here are the replies. Basic questions. Bioactivity. Incredible bioactivity. If you look at the compound, you would say yes. You have to do the analysis, but the complexity of the ring is really interesting. But at the same time, we have practicality and scalability in the synthesis. Here's the synthesis. Obviously, I'm not going to talk about this. You perhaps can observe why I've done this. First reaction, Robinson. Good. This could be done on gram scale, now it can be done on the kilogram scale. So this reaction has been known for 1 century. The next big step, where is it? It's here on this photochemical rearrangement, 1957. Okay, you go through, that's the point. There it is. The group made 500 milligrams. But just to make sure, obviously this could be common salt if he wants to fool us. But apparently what we have here in this is thapsic argon. So you can actually see the product. Now you remember Thomas Hudlicki and the Emperor's clothes. There was nothing in the flask. Now we have the flask being photographed and showing with the compound in it. Okay? I won't discuss these reactions. Anybody can get the article, and but there's a comment here. Thapsic argon is not produced in gram quantities because of its possible toxicity. That's just a lesson for us. When you know the compound you're making can have toxicity, bioactivity, don't make very much of it at one time. Conclusions. What is the diuretic analysis and the new direction? The key reactions are actually, first of all, this large group, several one-part sequences in which you get at least 2 reactions in the one part. The cyclized phase uses Robinson annihilation and the Barton photoreagent. But they've been used in a very, very efficient way. On the oxidase phase, there are 6 oxygen atoms around the 2 rings and 2 more in the lactone. But having 1 oxygen and planning correctly, you can use the first to make the second, to make the third, and go around the ring, putting in all the oxygens. Okay? Well, second compound, I've chosen strychnine, but not the wonderful Woodward synthesis. Here we go. Indole alkaloid strychnine, but I'm going to use the synthesis from the Chris van der Waal lab, which came out some years ago. Here we have the famous man again. He says, you made strychnine, but he made it in 1954, well before anybody else even thought about making strychnine, because the compound is so complicated that nobody else would even dream of trying to make the compound at that particular point in time. Great comment. If we can't make the compound, we'll take it. 50 milligrams is enough to kill you. So that was a kind of incentive to the students to make the compound. There we go, strychnine. There is the structure. At the time it was made by Woodward, it was considered the most complex molecule ever synthesized. You can actually count 1, 2, 3, 4, 7 rings. There's a bottle of strychnine if you're thinking of taking it. This is from the Larry Overman review, and what he does here is to show this. Why does a molecule such as strychnine create so much interest and enthusiasm that everybody wants to make strychnine? It's in the article. If you want to find out, have a look. Here we go. This is the van der Waal synthesis with only one student. Now that's another difference. Woodward's B12 synthesis with Eschenmoser, I think there's something over 100 people on the publication. Now you do a synthesis, 6, 7 steps, 1 student. Okay, so here's the student and here's the van der Waal. This compound really is commercial, but you can also make it. And the reaction, the key reaction, which I'll try and show, is what is called the creation of a zinc aldehyde. You take a pyridine, actually a pyridine salt, and you do a simple hydrolysis, and you make this part here in red, which couples on to the nitrogen. The nitrogen, and then you make this. Okay? Then you do basically an resolve the reaction. We'll comment on that. From then on, you're almost there to the final structure. Yes, there are a few reactions, finish up, you have to put in this unit, and then you get finally. Once again, my idea is not to discuss details of the syntheses. You just get the reference and have a look at it for yourself. What I'm trying to do is call your attention to what might be most important. So what is the secret of this new, efficient will show that, making strychnine in 6 steps? You'll see on the next slide why that is important. Here we go. Here's the kind of retrosynthetic analysis. Here's strychnine, you go back, this compound was already known, a century ago at least. And it's in equilibrium, and so you get the conjugate addition, the intermolecular disorder reaction, and here we have to have the pyridine unit which will create the zincy aldehyde, and this part is here. 1, 2, 3 simple substrates, and you get them together. The zincy aldehyde was a reaction which Van der Waal found 1904. The same thing. A very old reaction which none of us here had ever seen before. He found it and used it to make strychnine. And the IMDA reaction, the Diels-Alder intermolecular reaction, I estimate more or less in the 60s. We started doing this in Sao Paulo in the early 70s. But I can say we were not really original. So we're looking at the 2 key reactions are actually very old reactions. But they were used in a different way and in a different retrosynthetic analysis. Here's the summary. I have to mention things here because I know this is not very clear here. So what did Larry Overman do in his review? He wrote up this summary and outlook, which I think is fantastic, and showed us this table. So we start off with Woodward's synthesis in 1954. 29 steps, overall yield. You can see it, 0,002. In other words, nothing to see at the end. The next synthesis was Larry Overman himself, but 40 years later, he got the step count down to 25 and the yield to 3. We now get to the last 2. Van der Waal synthesis, 6 steps. We're going down, 29, 25, going down to get to 6 steps, but the overall yield, maybe only 2 to 3%. After that, Macmillan published another synthesis with 12 steps, but slightly more efficient. So you can see the trend. New analyses with old reactions. New sequences, much, much shorter. The overall yield not necessarily better. Certainly, with the comparison with Woodward, much better. Okay. Well, I've still got some time. I have a few examples to show you. Here we go with Tamiflu. Well, Tamiflu, officially it's called oseltamivir. In other words, this is the generic name and this is the commercial name for the same compound. They are being used to treat all kinds of influenza, starting with H1N1, but also others in this group. Okay? So, what happened? That Roche had a patent worldwide, and when there was an outbreak, serious outbreak, which started killing people all over the world, Roche did the obvious. The price went up. That's fairly obvious. The price would go up. And they claimed that they couldn't make the quantities necessary to treat people. Okay? So what did the US do? For the first and only time that I've heard of, they broke the patent. They refused to accept that Roche could do this with the world population. And the Americans do not like to break patents. Not at all. But this happened in this case. The reason itself is actually quite simple. Here's the compound we want to make. This is the drug here. And Roche was using these compounds here as starting materials. They were using shikimic acid and quinic acid. And they have 2 problems. They're expensive and they are not really available. They are available in smaller quantities. So they had a supply problem and a price problem. Once again, what Simon and Dr. Fez have talked about in the last 2 days. You have to check on these things. But Roche wasn't bothered because of the patent. So, solution. Here is the reply. You can see once again it's the same Hayashi I mentioned, the one-pot chemist with his synthesis. Okay? Here we have the product. We have the 3 compounds which are going to be used in a multi-component reaction. They will go into the reaction, and we have an organocatalyst based on proline, one of the most obvious standard organocatalysts. So where's the novelty? The novelty is here. Nobody had ever talked and said, our synthesis is not better than yours, it's quicker than yours. We do it quicker. And that's the important thing, because if you need something for treating influenza, you don't only need quantities, you want it to be quick, very quick, so you can react. So the point here really is spot economy, but the main thing is time economy. So this is from the abstract. I'll show a little bit of the chemistry, but the point here is this word, time. Okay? Here's the synthesis. You start with the organocatalyst. That's one of the first compounds that comes in, and you join this up. It's an enantioorganocatalytic 1,4 addition. It's a microreaction, more or less 1890s. Once again, a great old reaction with new clothing. Okay? There are several other reactions. Then there's a Wittig reaction, 1950s. A further intramolecular 1,4 addition. And at the end here, there's a bit of functional group manipulation and a reduction. But you can see the reactions here. There are very few reactions, and they're all very old, once again. What we're going to do here is, there are some comments from the introduction. First of all, time is money. We all know that. But you've never seen this particular statement in a scientific journal talking about a synthesis. But time is money. So there are some comments here, and he points out normally single reactions have what we call a problem, kinetics. And you frequently can't get these things to go faster than they want to go. So what he does here is one pot. The reagents are all together from the beginning, and this makes the reaction sequence much, much faster than if you try to do every one of these 5 or 6 steps independently. Conclusion. You can reduce the time. So here's the comment. Most of the previous syntheses took about 30 hours to make Tamiflu. It's done now in 60 minutes. And that is really another aspect which I think is tremendously important. We are not in a rush, but when you need Tamiflu, you are in a rush. And you need the Tamiflu today. Okay? He should make the final mark that Jameson has reported a remarkable 3-minute synthesis of ibuprofen. Probably everybody in this room has used this drug on several occasions. Okay? So this is 3 minutes using continuous flow. Okay. I put this in here just to remind us, what are the time-consuming operations in the synthesis of organic molecules? It isn't a reaction. The reaction is probably over in half an hour, 2 hours. It's the quenching, it's the extracting, and it's the purifying after the reaction. That's where most of you will spend the next day, all day, doing that. If we can avoid that, we can get things to work faster. And one pot does that, because we don't need to do any of this kind of thing until the end. So that's where the time economy comes in. Yeah? He also mentioned a little about, we have other economies, atom economy, step economy, in redox economy. That I've already mentioned. What I want to hear was just to remind us that the time problem in organic chemistry is not the reaction, it's after the reaction. Well, I mentioned before, Corey has a synthesis which he published, actually after, no, sorry, before. Here it is. He also made Tamiflu. He was also questioned, why did you make Tamiflu and publish it? Because you could have got the patent and made a lot of money. His reply was more or less obvious. At his age, money is not going to help very much because he's basically well over 80 when this was published. So he decided that money wasn't going to do much difference to him. So he gave Tamiflu to anybody who wants to make it. Okay. Here's the synthesis, Corey. What I want you to see is this. This is the only constructive reaction. It's the only reaction which makes carbon-carbon bonds. ESSO deals order using Corey's own organocatalyst, because then you can do it in anti-selective form, high, very, very high yield, and also great enantiomeric excess. So this is the key reaction, the first one. And it's also a very, very simple reaction. What happens is that we have the group here, and we have the double bond here. What we need to, so I call this throwing the in a kind of dance around the ring. You dance the functions around the ring until you get this double bond. You put in functionalities. If you look at it afterwards with care, you will see in fact that some of the groups go in and come out again without really doing very much. But you could count again. How many steps? One constructive reaction, then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reactions, which basically are just changing functions. So by the Hendrickson equation, this is a very, very poor synthesis. One step in 11, which is efficient. Okay? Well, here's the Corey Labson of Tamiflu. Starts with an enantiomer. It's the only CC bond construction. Then you do a series of very well-known functional modifications. The Corey lab has been using these reactions for a long time. They made the first prostaglandins using this kind of chemistry. Corey always he said he liked doing the reactions he knows well. When he likes the reaction, he uses it in all his syntheses because he knows it's going to work. Okay. My comment, if you look at this analysis, I would think that some of us, some of you, could perhaps maintain the first step constructive and reduce those other 10 functional group modifications, and you could perhaps plan a new synthesis based on Corey's. I think it's pretty obvious it should be done, as the molecule is interesting. Okay, well, I'm going to finish with this example. There are many others, but I think this is perhaps a good example for us to finish with here. We're talking about the sesquiterpene called artemisinin E. I know it's the second sesquiterpene, but it just happens to be a great molecule. The lady here, this person here, she won the Nobel Prize, Physiology or Medicine, 2015. Perhaps about 30 or 40 years after she should have received it. It took a long time to realize that she'd done a great bit of work. So here we have the lady and we have artemisinin. Now if you look at the compound, the way I do, I can see the sesquiterpene and I can see the monoterpene to make it. But that's not how it's made now. Anyway, but we can see, I can see in this structure, and we can see the most important thing, this part of the molecule. The carbon-carbon bond here has been broken and an oxygen has been inserted. So we have a ketal peroxy. It's a peroxyketal. And the biological activity is associated with this part of the molecule. That's what really does make this compound treat malaria. Okay? Well, a few comments. It seems like I'm going on with the things that Simon has said, but I got all this information from Sanofi because they are the company who's making artemisinin on a grand scale, grand ton scale to make artemisinin available. Some things about the impact. I think the impact to most of us is this is the estimated number of deaths a year, but I would say this is perhaps well over 1 million because you don't report adequately all the deaths from malaria as you should do. So this is obviously subestimated. I would say it's well over 1 million. And we can see here that the victims are mainly children. So that's the point which I'm trying to show here. Artemisinin, first of all, when I first saw this compound, it was called King Hao-Su. An American group went to China in the, I think, 60s and came back amazed that a country which didn't even appear in the literature had so much fantastic chemistry going on. This was perhaps the most important thing. This was used for a long time, this name, the Chinese name obviously, for artemisinin. Okay? Why should we synthesize this molecule much more efficiently? Because the isolation from the plant, and this plant can be grown in Brazil very easily, Artemisianum. I think it is being grown in Brazil, but it's not really a very efficient way of using this. Just a comment. My first PhD student, Mauricio, he did a synthesis in the 70s at the chemistry department in Ribeirão Preto. But these syntheses, academic syntheses, are based on the synthetic challenge, the structure, synthetic challenge, and art inorganic synthesis. But they just simply are not scalable. That's the whole point. So let's have a look at the question. This is also from Sanofi. You can think about getting artemisinin from here or from here. In other words, agriculture. You have to have cultivation. And this here has various problems. The first problem is that the whole process takes about 15 months to grow and do all the rest. If you do a synthesis, you can perhaps hope to get to the end in 3 months. So the time has gone down from 15, gone down to 3. And that is important when you're making a drug for malaria. Okay, a bit of the chemistry, which we'll see in more details, and a bit about the extraction. We have to make artemisinin, but we also have to make 2 analogues, derivatives, because the is sold as a cocktail of 3 compounds. The whole point here, this is synthetic and the way it's shown, it is just to tell you, when you want to get some information, you don't have to always get the original publication. You can go to home pages with famous chemists, and these you'll find all this kind of information about who's done what synthesis, where. I always like to look at some of these home pages to get all this kind of information. You can see Hans Reich, he's in Wisconsin, and that's what he offered to us. So, the syntheses now. We have some biological synthesis or synthetic biology. Now this may be a little bit of news to you, but this is very important now. We are doing synthetic organic chemistry, but using enzymes, modifying enzymes. So as far as I'm concerned, they're just different reagents, but it's a different kind of chemistry. And this is becoming more and more important to do this. So if the organic chemists can learn to do this, they'll get the jobs. That's the whole point. But if we sit around and forget it, then other people get these jobs to do synthetic biology. Okay? We also have we have a little bit of classical batch reactions and a photochemical continuous flow step at the end. So we have biosynthetic steps, or you could call metabolic engineering, We have some photochemistry, continuous flow, and even a couple of classical reactions. Sanofi is now produced on a large scale, but Novartis and Amiris are also more or less the same way. The scientific group of J. Kiesling, they are the group that are really active in synthetic biology. So if you want to find out what's happening, look at some of the references with J. Kiesling. Seeberger and Gilmore are doing some chemical, photochemical part of the syntheses. Now this publication which I found, it's actually published at the very end of last year, and it's published by a group in Wales, Worth and Alleman. And what they did here is to more or less repeat. So it's a kind of quick way to see the synthesis. Here we have farnesyl pyrophosphate. Very simple compound, and this is the precursor in nature and also the precursor here. You can treat it with enzymes, it'll cyclize. Then you can do with what they call engineered yeast. You then do an oxidation here to get this compound. Either one of these, you can do chemistry in the old word sense of the word, in which basically you're oxidizing once again here. You can get this compound, or you go straight here by simple hydrogenation, and this is the key compound. This dihydroartemisinic acid. You can also get it here. So we have a kind of collection of roots, and this compound then goes into the flow system to form artemisinin. A bit about the synthetic biology. The point I'm going to finish now is that I want you to see at least some of the question about synthetic biology, because this is not really news. But we're going to have to get involved in this if we're going to do synthetic organic chemistry. Okay? So we can see here, I'll show this in another slide later on, a little bit of the process. This is this publication on making semi-synthetic artemisinin. It's a model for using synthetic biology for making drugs and also making flavors and fragrances. The big fragrance companies are now making things like Valencine, which is a very high cost component of perfumes. They're doing it not by chemical transformations but by biological transformations. Okay, so that this is becoming more important. Sorry about that. Let's go to the next one. This is kind of interesting. You can see the start. All these steps here are enzymatic. Starting from perhaps farnesyl pyrophosphate or something else which is perhaps already in the system. Some of the syntheses do not start with farnesyl pyrophosphate. There's no need to. You can start with sugar, because sugar will make terpenes. Sugar will make farnesyl. So you don't even have to really have farnesyl pyrophosphate. You can put in simple sugar, because the system knows how to transform sugar into farnesyl pyrophosphate. Okay? So this is the sequence. I think I've jumped one. This slide I didn't really like very much. It's still here, but perhaps I'll just skip this. This is a recent publication by Seeberger and Gilmore at the end of last year. They've now got this. You can see the whole traditional way. Traditional pathway from the plants and the problems. And now the current work which they are doing. Basically, the end is more the photochemical reaction. Unfortunately, I don't even remember where I found this, so I feel a little bit. This is about the final photochemical reaction, but I'm going to skip this for 5 reasons. Now, this is a really good review by Garg and his colleagues. It's so new, we don't have the page numbers. And what he's talking about here is total synthesis with collaboration. Now, normally who does synthesis does not want to collaborate, he wants to compete. He wants to be first, but he doesn't want to collaborate. So he's trying to convince us to collaborate. And one of the examples is here. We have a complete view of the actual synthesis. The Kiesling and Sanofi Aventis are making artemisinin, and these compounds here are part of the cocktail. So you can get from here, by playing around with this group here, you can get these two compounds, and you can get the cocktail for use. What does J. Kiesling do? He starts with glucose, very, very available. Using certain enzyme systems, he can go to acetyl coenzyme A, farnesyl pyrophosphate. Just like to say Simon is leaving. I think maybe we should acknowledge his presence here, please. Yes, sir. Well, I'll just try and finish up on this part, and I promise to stop when I get to the end of artemisinin. We have the Kiesling group. This is basically, as you can see, using enzymes, starting with glucose, which is obviously very cheap, and you can go through this, and you can get some kind of idea of the scale. Now, fermentation process, etc., have a problem. It's difficult to get the scale up, but obviously industry is taking care of that. But it's not easy, because you have to usually work in rather dilute conditions. Anyway. And here is the Sanofi part. Okay, they start with what is made by the Kiesling group. Once again, they have the artemisinic acid, a chemical, classical hydrogenation reduction with the yield and the stereochemical relationship with the new center. And this is the key compound, really. You have to modify a little bit the carboxylic acid, and then you come in with the photochemical reaction. We react on this part of the molecule with light. You get in the hydroperoxide, and this undergoes a rather well-known further oxidation, which the overall yield is this. The most important things here. They made 35 tons in 2013. In other words, the synthesis is now viable for making artemisinin. And that is Sanofi with their semi-industrial process. So the only thing that's wrong with this photograph is there isn't a person there for you to judge the size, but it's big. It's very big, and this is where they are now doing the semi-synthesis of artemisinin, starting with that acid which I've mentioned several times. Okay, I won't go any more, okay? I could do. This was meant for Simon. You make Viagra, and the competition makes something very, very similar. We call it Me Too. Anybody here could plan a new Viagra. You make a compound that looks like any of these and probably has the same activity. But he's left now. He certainly wouldn't have liked this very much. Anyway.
Nós temos tempo para perguntas. I have time for questions.
Obviously not. The 1960s was kind of a mark in history. If you look at the situation in physical organic chemistry mechanisms, since the 60s when we had hundreds of books coming out, there's been perhaps a couple of books published. They don't sell anymore. And that is clear. I haven't got the kind of information how much was taken out of mechanisms and given to synthesis. But when synthesis lost its money and went to catalysis, the information is about 20 to 30%. Now that is significant. That means if you're doing a Nicolau synthesis and you knew 20 million, then you weren't going to get a grant. And that's one of the reasons, in fact, that they don't get any more grants, because the money of this kind of order has been taken out of one topic and gone to the next. But the next topic, you'll probably have more chance of guessing than I do. I think catalysts will be around for a long time, personally. It's perhaps the most important part of chemistry, as we all realize now. You practically don't do any kind of chemistry without catalysis. And that's perhaps the whole point. Sure, sure. What? Sure. Already here.
It's already here, but it is seen as general. But computational science will then so to be able to capture all data also, because human brain can process
Well, perhaps a final comment. Understand, because I didn't say anything about this. What is the final message for you? Well, these old syntheses done by, Kishi, Nicolau and colleagues, there was a comment, which was there actually, that this was a fantastic training for the people to go into the pharmaceutical industry. And that's a lie. Because you can do a 2-year postdoc with one of these people, and you do the same reaction, the same reaction, the same reaction, and you don't learn anything. You just get bored, because that reaction has to work. If you're lucky, you might do 2 or 3 reactions. In these new syntheses, you can see it's the professor and a student. He does the full synthesis. So he learns a lot more doing this work, a small synthesis, than the old style. And of course, as far as I'm concerned, it's going to be much more useful and obviously employable with this kind of training than the old style training which was given maybe 30, 40 years ago. So I think this is good for you. You're going to learn more, see more, and therefore be more useful to the new pharma industry, fine chemical industry. I didn't really say that before, perhaps it wasn't really obvious, but I see that as one of the bases. This work costs a lot less and trains a lot better. And that is, for me, is really important for the future. Okay? Any other questions? No, so I was hungry, so it's